All right, good afternoon, everybody. Welcome back from spring break. Before we get started, does anybody have any questions? All right, let's jump in. So today we're going to talk about modeling a mass spring damper system as an RLC. And so this mass, we draw it square, and we're drawing it kind of like it has some dimensions. But mathematically, that mass is just a point, right? We look at this spring as if it's got some kind of physical space, but really, that's just another, you could call it a point spring. Same with the damper. Okay. Now, in reality, these things do have physical dimensions, but it's no different than when we're talking about resistors, capacitors, and inductors. And what we're going to do is we take a diagram like this, turn it into an RLC circuit, and then see if it's over, under, or critically damped, and analyze things. So we have a mass, and this is the force of the mass, and we're going to model forces as currents. Okay. And you can see where that current is a derivative, right? Then over here for the spring, we're integrating, right? And so that's the current of an inductor. And then a damper or a resistor has no memory to it, so it doesn't have any frequency or time domain dependence on it, all right? But now in the book, it has the forces. So, the force of the damper is going that way, spring is going that way, and the force of the capacitor is going that way, so they should all sum. But when you see a mass, all you have to do is draw a capacitor and just automatically tie one end to ground. Springs are easy to draw as inductors because they almost look like inductors. In fact, you can take a wire and wind it yourself and turn a wire into an inductor. And then the damper gets turned into a resistor. Now, conveniently enough, the mass just equals the capacitance, but the inductance is actually 1 over the spring constant, and R is an inverted thing as well, and that's 1 over the damping coefficient. All right. Something else that we can't forget about is that if you have a fixed surface, that's actually going to be ground. And the thing is you can see that this mass is not connected to ground physically, but one end will be, because essentially the voltage across that capacitor is going to equal the node the node voltage here, which will represent velocity. All right. Now something else besides just changing mass to capacitor, spring to inductor, damper to resistor is that it might look like we're looking at voltages here, but in fact, it's velocity. All right. And then, which is here. So this is what we'll be solving for. And then if you want position, you have to integrate to get that. And if you want acceleration, you take the derivative to get that. All right. Probably best just to do some examples. But are there any questions before we move on? All right. So before we move on, I should just point out, I know maybe this course isn't known for using the book, but really the treatment here in the book really can't be improved upon. And so I follow it pretty well. All right. And if you're looking for extra problems to solve, the problems, chapter problems are great. Okay. So we have a moving platform, right? A spring, a damper, and a mass. Now, physically, what could this be? It could just be, here's a tire, right? Going, I'll just into some kind of spring, and then a damper, and here's the mass. Now, what could that be? That could be 1/4 of a car. And while you might have a velocity from left to right, if you hit a curb, we're going to have an instantaneous velocity change upwards, right? Or an instantaneous position change, okay? So anyway, you can model a car going over a curb. And you can assume that 1/4 of the car is going to act like the whole car. That's all we have to do. So first rule, the mass becomes a capacitor. One end we just tie to ground. That's just what you do right off the bat. All right. Then we have a damper connected to the mass. Now, if I connect the damper, let's just go off to the side here. All right, if I have a capacitor and I connect that to ground, and then I go connect the resistor, right? That end of the resistor is tied to ground. So you never do that. You always tie these components to the other side. Okay. And what's Vy? It's the velocity of the mass. What's Vx? It's the velocity of the moving platform, right? Then we have a spring. And we have Vx. So Vx is the input velocity, which is the voltage, right? Vy is you could call it the output velocity, right? And that's the capacitance, the voltage right there. Now that moving platform, see, it's connect directly to that spring. So when that platform moves up, no matter what's going on, right, that input is right there, right? An ideal voltage source will, whatever the voltage is here, will appear here. And that's how we're going to assume things. All right. So A lot of times it's not as important to draw out the waveform as it is to know what kind of waveform you're going to get. All right, you know, is the system going to be over, under, or critically damped? All right, so let's come up with a system model, right? So this is the inductor, and ZL is going to be SL. ZR is going to equal R, and ZC is 1 over SC. All right. Now, you can use mesh to solve this, where you sum all these to 0. You can use nodal analysis, right? But there's still 2 nodes that you have to solve for, and you're looking for that voltage. I prefer to do the simplest thing, and that's basically voltage division. And so our transfer function, right, it's going to be the impedance of the capacitor divided by the sum of all the impedances. Okay. All right. Now, on exams and things, drawing, usually the way it is drawing this picture is usually 1/2 of the problem, all right, or 1/2 the points, all right? And then the next half would be coming up with the transfer function. This isn't, just as a reminder, right? That's not really a transfer function, it's just some impedances. We have to put it in the proper form, all right? So ZC is 1 over SC, oops, right, divided by 1 over SC plus SL plus R, all right? If I multiply through by S, I get 1 over C plus S squared L plus SR. All right. Now, this equation, it's true, but it is not in the proper format. And having it in the proper format is critical so that others can understand your work and that you can easily find whether it's over, under, or critically damped. All right. This is true. And yes, we could come up with our over, under, critical damped response from this, but still it's not in the standardized format, and so we need to keep going. And what we do is we pull out an L, okay? And then now I'm going to write it in the standard format. And that standard format, right, the highest polynomial comes first, then the second, and then the last thing is 1 without any term of S, all right? This coefficient here, you do whatever it takes to get that to 1. This is the standard format. Now, what you might not realize is completely generic. We have this equation. You can see 1 over omega naught squared is LC. And 2 damping coefficient omega naught equals R over L. Now this is strictly for when these elements are connected in series. Not every RLC circuit will have this same denominator. All right. But now to determine whether it's over, under, or critically damped, you don't have to put it into this form, right? But what I'm saying is once you're in this form, you can see much more easily the generic form, and you need to be able to go back and forth. All right. So let's pick a new color, right? And I think I'll just, so the poles are the roots of this polynomial, right? And the roots are given by this. Now, since all these values are real, right, we can simplify things a little bit. And we only have to worry about this right here, because if b squared is greater than 4ac, two real roots, really poles, right? If b squared equals 4ac, two repeated poles, right? Because if this is equal to each other, oops, you get minus b plus or minus. And even though it's 0, it actually, you're adding 0, subtracting 0, you get the same number. There's two of them there, right? And then if b squared is less than 4ac, complex, right? And so this would be the over critical and the under damped response. All right. Now, I have officially run out of room on this slide. Just let me refresh my memory. 100, 100, 100. All right, I set everything to 100. So R equals 1 over B. K equals, L equals 1 over K. And C equals mass equals 100. All right, so what's R divided by L? 0.01. Okay, so B equals 1. Conveniently enough, B squared equals 1 as well. Uh, 1 over LC. I know it's supposed to be 4 over LC, but I want to calculate that first. So we have 1 over 100 times 100 equals 1. And so we have complex roots. So let's just draw that out. Okay. I'm not saying exactly where it's at, but I have a pole here and a pole here. And I apologize is that when I say complex roots of basically the denominator of h of s, it's really complex poles, all right? I find that I've been trying not to mix up those terms, but it seems kind of impossible for me to fix that, but I'll work on it. So let's go look at, so the thing is now, if I wanted the step response of that, right, if I actually wanted Vy of t, that would be the inverse Laplace transform, right? There's the step. Okay. And now that you know they're complex roots, when you do the partial fraction expansion, you know to use the complex roots one. Now, shall we say that that's a lot of work, right? And you can kind of, sometimes what you really want to just know is, you know, how it's going to act, not exactly how, all right? So when you have complex roots, right, the step response is going to go and it's going to ring and then eventually kind of peter out, right? And we really kind of have something proportional to e to the minus t omega naught, right, times a sine, and there's something in here that is basically telling you where the peaks are occurring, right? But this kind of almost looks like a low pass, right? And it's not exactly 5 tau, right? Which would be 1 over that omega naught, but it's actually pretty close. So 1 over LC equaled omega naught squared, right, equaled 1. So that means omega equaled 1. And again, a second order system doesn't have a tau so much, but it does have this exponential decay when it's underdamped. So the thing is I'm thinking, yeah, it should take maybe 5 tau to get where it's going. All right. So I wanted to see what was going on in LTspice. All right. So we said the resistance was 1 over the damping factor, 1.01, 1.01. The capacitance was 100. And that means really it should take around 5 nanoseconds to get where it's going. Now I'm just going to double that. Okay, because I really don't know when the ringing is going to stop. All right. And what you can see is that I have more than one pulse going on, that it goes on, and you can see it overshoots and then undershoots. And in fact, it hasn't quite stopped ringing. So I'm just going to make it 20. All right. So really, because of the overshoot, yeah, 5 seconds, it's certainly over 1, but it takes a while for it to settle, right? But you can see that, yeah, maybe in this case is about 10, it's finally settled down, all right? But what I'm trying to say is that calculating the exponential decay of the actual real part of the root, right, gave me enough estimate to kind of guess where this should be, right? And if you really, what I do is I just look it up on the Laplace transform table when it's complex roots, and you can figure out exactly what the frequency of this term is. And this is modified a little bit as well, if I recall, to the damping coefficient. All right. But you can kind of plot it roughly by hand. All right. Now, yeah, it's not really a step response because it's really a pulse response. So if I just keep it up for 40 and I only went, you know, that's a real, I must have made a mistake. Here, we'll just run it for 20, right? And there we would have our step response. And we know that there's going to be overshoot because we predicted that it was underdamped. And the thing is even, where are we? Okay, so when we use the proper, when we put everything into this form, right, that damping coefficient, which will tell you what the ringing is, there's omega naught, which tells you about, you know, inversely how long it'll take to decay, right? This equation will give you a rough idea of what to draw, all right? Okay, so that's one example. Okay, now those are the RLC examples, but it might be helpful just to conceptually look at what's going on. So if I have a moving platform, right, Vx, and I'm not going to put the t any longer, right, velocity of the platform, right, and now I'm just going to put it into a damper only, and then I have a mass. So there's my platform. That's like my input voltage, and I'll label it Vx, right? It goes into a damper. Dampers become resistors, right? And then I have a mass. If I just tie this end to ground, really Vx is just going to be whatever this is, and there'll be some constant current. So it's got to go into the non-grounded side of the capacitor. All right. Well, that's the low-pass structure that we've seen for a long time in terms of resistance. Okay. In terms more like you'd be used to plotting it in a Bode plot. All right. We would have that. All right. Now, let's ask ourselves some questions. What if that damper broke and it was disconnected, right? Well, you'd kind of have your platform. You would have your mass, right? And there'd be no connection here. Now, which would be something like this, right? And so there's no way for this Vx to affect that mass, right? So it's disconnected. However, if you did have a platform and then the thing is being held up by the damper and it disappeared, this mass would fall down on top of the platform, and then in fact, Vy would equal Vx, right? What if right, these dampers, you know, they need to be lubricated and they can freeze solid so that they don't move, right? So, right, resistance equals 1 over B, right? And so if that froze solid, right, it's not damping anymore, right? So B would equal 0. Wait, no, that's not right. It's not damping anymore, so B, it passes it perfectly, so B would be infinity, and then R equals 0, right? So if that damper isn't there almost, but it's just like one solid, it's not damping anymore. It's just acting like a post, okay? So if it's an inflexible post with no spring or no give, right, then the mass might as well be here, and Vy equals whatever Vx is, right? In this case, if the damper just broke and went, was missing, right, then B, it's doesn't pass anything, and then R would equal infinity. And so if you had a resistance here and set it to infinity, basically it disconnects those two parts of the circuit. All right. But really, so anyway, H of S 1 over RC, S plus 1 over RC. All right. Now, remember, this is velocity. And so how do I get position from that, right? Well, XT is position, or what they call displacement, right? Well, velocity is what? It's dx dt, and then the derivative of that is acceleration. All right. So if we're given this, right, then xt we just have to integrate. All right. To find acceleration, yep, we just take the derivative. So here we have, nice easy numbers, 1 kilogram and a damping coefficient of 1. So the resistance is 1. And so essentially, tau is 1. So for a step response, it'll take 5 tau to rise to where we want it to go. All right. And so if we want to know how does the velocity change over time, that's Vy. And you can see the step response. Now, if I want the acceleration of that, well, I just take the derivative of that. Okay. And these are behavioral voltage sources where ddt is the derivative. And if I want the displacement, idt is the integration. And actually, I should have called that it's really the displacement of y, not x. All right. And so when you have a step input of velocity where the velocity goes from 0 to 1 and then never goes back down, well, yeah, your position Where's Vy? Just it exponentially gets up to speed, and then your position is just linearly changing with time, right? Your acceleration, yeah, you accelerate rapidly, but then you're no longer accelerating, you're at a constant velocity. So integrating a constant velocity gives you a linear time frame. And so that's the relationship between all those. Now, what does that mean in the frequency domain? Okay. Well, so if I take Vy, Vx, right, and multiply it by S, see you. Just let me finish this thought. Okay. Multiplying by S in the frequency domain is the same as taking the derivative in the time domain. And then if I need to take the integral, right, I haven't forgotten you. I multiply by 1 over S, and that's taking the integral in the time domain. Yep. Why don't I review that right now? Okay. So in all these problems, right, there'll be some box with mass. That gets turned into a capacitor, and one end is tied to ground. All right. Then there'll be if there's a spring, something that looks like a spring, that gets turned into an inductor, and then the damper gets turned into the resistor. So what would the picture of this been, right, is I would have had a moving platform with the Vx. It would have gone into a damper. And that would have been the mass. Okay. So there's the moving platform. That's the input voltage. There's the damper. That's the resistor. There's the mass. And there's the capacitor. Did that answer your question, Mike? Oh, yeah, Ed.
So can you explain again why the S, multiplying by S is the derivative, but multiplying by the reciprocal is the integral?
I mean, there's an intuitive explanation, but really, you kind of got to go back to the Laplace chapter if you want like the full mathematical definition, how that works. But kind of because it just is. Okay. I know that that's not necessarily, the most satisfying answer. But if you look at the Laplace transform, right? Oops. All right. F of S, right? We're going from 0 to positive infinity, right? Let's see, we have xt, e to the minus st dt, right? Well, here's the thing. What if xt is a step, right? We have that, right? And since we're starting at 0, right, this effectively becomes 1, right? Which really becomes, oops, 1 over s, right? So here's the thing. Where's the integration come from? Right from the Laplace. You know, here's our integration. The simplest thing is 1 or some, you know, some constant, right? And this function that we're integrating with gives you 1 over s, and so that's the integration, all right? Showing the derivative is really beyond today, and to make sure I didn't screw it up, I'd have to go look it up myself. But intuitively, let's take a high pass filter, right? Well, when we're in this regime, right, it's really S, right? And then over here, right, we have S plus some number. But omega is much, much bigger than 10. So we really kind of have infinity or equals 1 or 0 dB, right? So in this region where we're rising up is S. And if we recall, right, high pass filters detect the edges, right? So if I put in a step, I get this exponential decay where hey, there was an edge there, and then it decays. So that is like taking a derivative, right? Now, let's just, what if this was like, you know, 10 gig, right? That would mean most of the frequency range, it's just acting like you're taking the derivative, right? Because if omega is a lot less than omega naught, you get S, or no, sorry. Yeah, you get this. Okay. Did that help, Ed?
Yes, thank you, Professor.
Do you want me to get the answer more detailed for you later?
Yeah, later I think would be best.
Okay.
Yeah,
All
thank
right.
you.
All right. Still, it's a really thoughtful question, and thanks for asking it. All right. Any other questions? Okay. All right. We did that. Okay. So far today, we have dealt with a system with one pole. Okay. All right. That was our R secret, our RC configuration where there was only a damper and a mass, right? And this is at omega naught, right? We did complex poles, right, where it was an RLC and we okay, and so we had 2 poles here, but we haven't really talked about now. Yeah, you can have, we didn't do critically damped where we would have 2 poles at the same spot. All right, but let's go back, and we removed, in the RLC circuit, we removed the inductor. Let's remove the resistor and see what happens. Okay. So here's our platform. Right. Now we have a spring, and we have a mass. Right. We have the velocity of the platform, the velocity of the mass. Let's see. Let's even draw it. So here's our voltage source, right? Referenced. We're moving all our references to ground, right? Then we put it into our inductor. Then we put it into our mass, and then the other end of the mass is tied to ground. I tend to draw it, sorry, I should make that more inductory. I'll draw it like that. All right. What I did is I just kind of bent this and then bent that. All right. But kind of, maybe that'll help you visualize what's going on. So HS equals the ratio of the 2 velocities in the S domain. And that's really just a voltage division. So we have the capacitance impedance divided by the sum. That's 1 over SC times SL. Let's multiply through by S. Let's pull out the inductance. All right. So the poles, or the roots of that, is still minus b plus or minus b squared well, A is 1, there's C, B equals 0. All right, so really we get plus or minus 4 divided by LC, right? Square root of 4 is 2, the 2's cancel, and then, so really, we have our poles there. I'll keep it in blue. And now they have no real part. It's all imaginary. Now the thing is to actually where is the energy lost? Well, if I put in energy into this system, well, there's no resistance. There's no real power loss. Oh, sure, some of the energy will be stored in the capacitor, some will be stored in the inductor, right? Same with the spring. Some will be moved in the mass of the spring moving, or some of the energy will be in the spring, right? And it's almost a case where you have a pendulum with no friction, right? It's up here, it's all stored in potential energy. Down here, all the energy is stored in kinetic energy, right? And so what will happen is you're going to get an oscillation and it'll never stop, all right? So you might not know the exact phase or whether it's a sine or a cosine, but it's just going to oscillate, okay? We'll be getting into this into more detail where if all the poles are out here, right, where there's a real part is negative, you're going to get some power loss, and so things will decay. But when you have things that are purely imaginary, you're going to have a sign. And then if you have poles on the right-hand side, right, meaning what if we have omega naught S minus omega naught, right? The inverse Laplace of that is going to be to the omega naught t. That increases exponentially rather than decays. All right. And so if a system has its poles here, it'll be in control. If it has any pole on the real 0 or greater, right, you'll get oscillations if it's exactly it's only imaginary, and you get exponential increase for any real pole. And so those are what are called out of control systems. All right. So if I had a damper here, right, that would actually provide a real part to it. And so it would stop oscillating, right? But if this was if I was modeling my car suspension, right, and this damper broke and just fell off, then I'd be left with this. Or even if it didn't break, but let's say it just kept getting weaker and weaker and weaker. Every time I went over a bump, right, my car would start oscillating. I don't know if you've, and if it was really gone, it would oscillate. And if you were in a vacuum, your car would go up and down forever, which is kind of annoying. Any questions on that? Okay. So we have reviewed a little bit the poles and the roots so far as we've gone along. And so what I want to do is just sorry, this is annoying me here. All right. So here, what we've got is the damper is inside of the spring, and so it's in parallel. And an example in the book is right there. So draw the equivalent circuit. You have the voltage source. These are in parallel. The mass is tied to ground. Then deriving H of S, right? And then you just write out the conditions: over, under, and critically damped in terms of R, L, and C. But you don't, everything is generic. You don't have to solve for anything. All right. Here, okay, it's a little bit trickier. We have a moving platform. The inductor is connected straight to the mass, and then you have the mass connected to the fixed surface. Now don't be fooled, right? One end of this mass is connected to ground, right? And so what you can have is more than one connection to a mass, right? And then one other side of the damper is connected to a fixed surface. So the idea of ground isn't like a position, it's really a surface that doesn't move, right? And you can have ground, anything that doesn't move with respect to the direction you're caring about is effectively ground, all right? But again, you draw the equivalent circuit, transfer function, and then is it over, under, or critical? Now in this case, we have a series connection, right, which we actually did. I give you some constants, right? You calculate whether it's over, under, or critical. And then, yeah, in this case, you're going to plot out the velocity, right, of mass over time, plot the displacement over time, right, which is you need to integrate, right? And yeah, it's probably good to use LTpsice for this, right? Or you can do it. You can do it in Python. And then this is from the next section, but essentially you have a seat and then you have a person, and the person is broken up into a series of masses, springs, and dampers. All right. So that's, I think I kind of hit just about everything you need to do to be able to do the homework. If you look at the exams, it's usually like a question 1 or a question 2 type thing, or 3, maybe 4. All right. So it's pretty heavily linked. Okay. And so these are all like valid, what you could say, plots, RLC circuit implementations of possible configurations, right? This one's in series. This one they're in parallel. Okay, here we briefly touched on it. You could have a damper connected to the mass, and the mass is connected to a fixed surface. That's why it's connected here and here. VX will always be telling you what the moving platform is. And this mass is just drawn out so that you can see the connection of it. Oops. Sorry, this one goes to that one. All right. All right. Now, yeah, switching these two in order doesn't really matter to VY. Switching this one on top doesn't really change that circuit. And this really has these configurations. And so as far as RLC circuits, those are kind of the where you have one R, one L, and one C. Those are kind of the major configurations. Now, sure, if I put a damper here, fixed to ground, that'd be like putting a resistance in parallel with here. Same thing here. If I put, a spring or a damper, that would put it in parallel here. I could put another resistor here. But really, these are kind of the four major configurations that you can familiarize yourself with. Just as a hint, though, these all have the same denominator, right? These kind of come in the parallel configuration where you have that. This one has the series configuration. Right. Now, yeah, you can put other things in there, but most people do pretty well on this. And the thing is what's great is that you could be designing some kind of electronic control system for your car or a car, maybe not your car, because you're going to take public transportation and save the planet, right? Where's my... But is that you can be designing, I don't know, maybe this isn't a good, you have an electric motor working with a robot, right? But that robot has some kind of physical system, right? Now, case in point, that you can have, this is the top view of a disk drive, right? And the data is all stored on top, and magnetic changes, right? And that there's a read head, right, picking up the magnetic vibrations, right? So this has got to move back and forward to get the track, and then yeah, actually it just has to move back and forward. It's not gonna, and then it'll spin to where it gets it. So this physical system, right, this could be the moving platform, or let's just say this is here's a moving platform, and I have just drawn a kind of like a rod, and then the mass is at the end. Well, there's no damping coefficient, you might say, but these, parts, right, they bend. If you wiggle a metal rod back and forth, it does kind of spring back and forth. And so you could be using your control system like a microcontroller, right, controlling the position, but this thing is kind of, is the system overdamped, underdamped, critically damped? Could be really important to your design. And probably if you try to interview at Western Digital, right, and talk about that, also that could help you land that job. But also the project here in this class, or the 110 lab, PWM digital to analog converter. Well, the microcontroller is telling this where to go. Well, you got to convert that digital signal to an analog signal. And in fact, right in one of their schematics, they're using a PWM DAC to do that. All right. So you can link all that into a thing that Western Digital makes hard drives, although that's not really what they say. They kind of enable everything. They don't say we're a hard drive maker. They say, we're enabling life as we know it. All right. So before you go to an interview, do read what they say they do at their high level, because it shows that you care. All right. Because our students are pretty good, and so then they're trying to determine, well, who really cares about Western Digital? And they're just, well, who looked it up? Things like that. That's about it for today. Any final questions before we leave for today? Okay, so this homework is homework 10, and it's due Sunday, but so is the other homework, right? So you just have to make sure you pace yourself to get these two homework assignments done in time. All righty, if that's it, take care. Have a good day.